Thank you. Hi, everybody, and thank you for joining. That's a huge audience. I feel a little bit nervous, to be honest. But let me start by checking the temperature. Who of you guys are front-end engineers? Show your hands. Nice. And who are designers? Great. Nice to meet you all. And I'm Anton Lovchikov, a product designer at Civil Martians. I became a color enthusiast relatively recently. Before that, for a long time, I took colors as a way of expressing my artistic ideas without thinking much about color nature. Who cares how colors work as long as the final result looks nice and gains likes on Dribble, right? And it was a valid conclusion back in the days. But nowadays, the requirements to the interfaces are much higher. An interface still needs to be nice and gains likes on Dribble, but it also needs to be accessible, easy to read, in other words. It also must be some kind of customizable, because it's an uprising trend of recent years. Take Android, for example. And finally, it should have some kind of distinction from competitors. So today, I brought you a technology that helps you to keep the contrast of your interfaces in check, which makes it much easier for people to work with, #accessibility. And it also allows you to build interfaces with dynamically adjustable colors, which provides an infinite opportunity for your end users to personalize and customize the interfaces. And finally, it gives you 50% more colors, which gives you more rich and deep look and helps you to stand out from the competition. And the name of this technology, I hope you guessed, is OKLCH. Why so many hype around OKLCH? What's so special about it? Why good old RGB and HSL are not enough? Let me answer this question by demonstrating you a small demo that I prepared specifically for this talk. Here are two pieces of the interface, exact pieces of the interface. The one on the left I built with OKLCH colors, and the one on the right I built with HSL colors. And I set up these colors in a way that both of these pieces look exactly the same when hue is set to red. And now I'm going to gradually change the hue parameter of each of these colors. And take a look and make a note how OKLCH manages to keep the contrast and readability of the interface, and how HSL version at some values of hue drops the contrast to almost nothing. I want to highlight it that I only change on the one parameter, hue. I don't touch lightness or anything else. Wonder how it works? Well, I'm happy to explain you how. But first, let's get back to the times when OKLCH didn't exist yet. I became a UI designer in 2005, and my first graphic editor, it was Macromedia Flash, but it was a huge mistake. So my first graphic editor was Photoshop. And it wasn't a great fit for UI design, but I didn't have much choice. Who of you guys used to use Photoshop for UI design? Show your hands. All right. So a lot of dinosaurs out there. Let's hang out together after the meetup. I'm sure we can share some cool stories. So I was an inexperienced designer back then, with zero knowledge of color theory and stuff like that. And when I saw Photoshop Color Picker, I had no idea how to use it. I mean, obviously I could grab the color prop and move it around, and so on. But I wanted to do it purposefully. So I used the most obvious, straightforward, and dumbest strategy that I could ever come up with. I grabbed the color probe, and then I stamped it right into the corner. And then I slided across this rainbow stuff, whatever, trying to find some nice-looking color. And while I was doing all of that, I discovered that for some mysterious reason, some colors went out dark, and some colors were bright. Did you notice it? Yeah, I'm sure you are. But those who are like, what's a big deal? That's kind of obvious that some colors are darker, some colors are lighter. What's the point? Just think about it. You are doing nothing to a color except for changing its hue. You don't want the color to be lighter or darker. You just sliding along the spectrum. But the observed lightness of the color dances like crazy. Doesn't it look strange? Back then, I knew nothing about accessibility, about contrast calculators, and I could only trust to my own eyes. But today, I can quantitatively prove that blue is the darkest color of the spectrum, and the yellow is the lightest one. Here you can see contrast score calculated with APCA formula. And this difference is so huge that we can easily read yellow text on top of a blue background. But why? Why blue is so much darker than yellow? I was attached to these stranger things for years, and I found the explanation literally just a couple of months ago. And I will share it with you, but please don't fall asleep within the next 15 minutes so you don't miss it, because the answer to this question is a key to understanding what's so special about OKLCH. Back to 2000s. Over years of practice, I developed some special sense of color. Every time when I needed red, I would mix in a little bit of white to overcome its over darkness. I would tone down the green, overly bright green, and I would shift towards cyanish color instead of using pure blue. What about yellow? I hated yellow. Every time when I needed yellow color, I would push it down to red, because orange is a good guy. Yellow is a little bastard. But the real pain came in every time when I needed a pale color palette. It required so insane amounts of labor-intensive manual work to compensate for all this color inconsistency that even a tiny wrong move could throw a color out of the line, making it inconsistent with others. So, and I struggled with these problems like every day for 15 years. I invested a lot in all of that. And now I have a question to Photoshop. Why does your color picker require so much manual work? And I blame RGB-based color models, such as RGB itself, HSL, HSB, and in fact, all these color models are used even in modern color pickers in modern graphic editors such as Figma and Sketch. Let's quickly sync up on this term. Color model is a mathematical way of describing a color with some numbers. There are a lot of color models out there, and all of them do the same job. They take objectively seen color and define it with 3 or 4 coordinates. The most popular, widespread color model is RGB. And it defines a color with 3 coordinates, red, green, and blue. By mixing up red, green, and blue value in different proportions, it produces the whole range of colors. Sounds good, but in fact, RGB is very inconvenient to work with. In real life, we want to do basically 3 things to a color. We want to make it darker or lighter, we want to make it less or more saturated, and we want to play with its hue without side effects. And none of this task can be performed by using pure RGB. Look at this color picker in RGB mode. I have no idea where to move the color probe in order to make color darker, for example, without messing up hue or without changing the saturation. And in order to make RGB a little bit more convenient to work with, engineers invented HSL or HSB, which is very similar color model. HSL defines the same, absolutely the same color, but with 3 different coordinates. Instead of red, green, and blue, it uses lightness, saturation, and hue. And having these 3 coordinates is very convenient. Now I know how to change the lightness, how to adjust the saturation, how to play with the hue, and the most important part, I can do it independently. When I change the lightness, it doesn't affect the saturation. When I play with the saturation, it doesn't mess up the hue. When I adjust the hue, it doesn't alter the lightness. Wait a minute. It looks like HSL is the perfect color model. Why do we need more? You know what? Screw OKLCH, use HSL, thank you for coming, see you in the bar. But before that, let me check something. Looking at gorgeous 3 coordinates of HSL, we can expect that 2 colors with the same lightness value will look, the same. None of them will be darker or lighter because the lightness value is the same. Well, let's try. Here is blue, 50% of lightness. Here is yellow, 50% of lightness. So we can expect that the text of that yellow on top of this blue won't be readable because lightness is the same, because none of them is darker, right? Let's check if it works this way. No, it doesn't. Of course not. Despite the fact that the lightness value of these 2 colors is the same, HSL says us, we still clearly see that blue is much darker than yellow. And it means that HSL neither explains what we see here, nor it helps us to fix this difference. And that's exactly why HSL version of my demo didn't work. I didn't touch the lightness value of all these colors, I just changed the hue, but you saw that contrast of the interface dropped to 0 at some values. And it means that you can't really trust lightness value of HSL, because it's not lightness, it's a lie. So for us to find the real reason of this yellow-blue inconsistency, we need to go deeper to the physics of light and human eye perception. That's a very complex topic. I'm just at the beginning of getting into it, but I found 2 key components that contribute to the way how we perceive colors. And these are light wave sensitivity and the display technology. Normally, without any conditions, human eye perceives green as the brightest color of the spectrum. And this feature describes by luminous efficiency function. Well, green is the brightest color of the spectrum, but we clearly see at our monitors that yellow and cyan are even brighter. What can explain this? The display technology. You know that each pixel on our displays consists of 3 subpixels, lamps, of green, red, green, and blue color. By lighting up these subpixels in different proportions, display creates all the variety of the colors. In order to make green, red, green, or blue color, so-called primary colors, the display lights only 1 subpixel. 1 subpixel means that only 1 unit of light comes into our eye. In order to produce yellow, cyan, or magenta, the display needs to light 2 subpixels at the same time. 2 subpixels means 2 units of light coming into our eye, which we perceive as brighter color. So let's recap. Blue itself is not very sensitive for our eyes. Moreover, the display lights only 1 subpixel in order to make it. Yellow, on the other hand, is a product of 2 subpixels, one of which is of green color, the brightest color that our eyes can see. Now you have the answer why blue is darker than yellow. So next time, give this puzzle to your friends at a party and then triumphantly proclaim, it's all physics. So now when we learned that our eyes prefer some colors over others, and the displays make some colors brighter than others, we can finally talk about the thing you all here come to listen about, the OKLCH color model. OKLCH is very similar to HSL in a way. It uses quite the same set of 3 convenient coordinates: lightness, chroma, and hue. Hence the name. L stands for lightness, C stands for chroma, and H stands for hue. What does the part OK stands for? I'm not sure, to be honest. I take it as awesome. Awesome lightness, chroma, and hue. But despite the fact that OKLCH uses quite similar set of coordinates, they work the whole way different. Here are two spectrums of colors produced by OKLCH and by HSL. OKLCH spectrum is quite irregular, but for one good reason. OKLCH distributes colors inside its spectrum according to observed features of colors. Instead of, stretching up the colors and filling the cube. But don't be confused by the form of OKLCH. It doesn't mean that OKLCH is a kind of truncated version of HSL. OKLCH contains all the colors that you can find inside the HSL cube. And don't be scared by this mountain-like looking spectrum. When I first saw these ridges and hills, I got scared. Where is so familiar and comfortable cube? I want it back. But the more I worked with that, the more I realized that actually the cube is scary. Our world is far from ideal. It's not cubic, it's not orthogonal. There is no much sense in squashing everything into the cube. So let's see how exactly OKLCH distributes colors. I'm going to take 2 slices of colors at yellow and blue values and inspect them. The most interesting part here is the peaks of these 2 triangles. That's the point of the brightest blue and the brightest yellow. As you can see, lightness value is quite different for them. Blue is a darker color, so the lightness value of blue is low. Yellow is a bright color, almost white. So the lightness value is very close to 100. And this difference in lightness value perfectly explains what we see here. We can read yellow text on top of a blue background because of huge difference in lightnesses of these two colors. Let's consider another colors. That's hard to read, right? Your eyes, I think, bleeding right now. But before I switch the slides, please take a note that lightnesses of these two colors are exactly the same. And that's the first superpower of OKLCH. It explains and predicts if combination of two colors will be easy to read or hard to read based on the difference between lightnesses of these two colors. Let's now see the second superpower of OKLCH is ability to fix the contrast issues. I'm going to take two slices of purple and red from the previous eye-bleeding slide. Lightnesses of these two colors is the same. Hence the contrast issue and accessibility issue. And OKLCH makes it very easy fixing it. I just need to reduce the lightness of the purple and increase the lightness of the red. And now this text is much easier to read. It's much easier to read on this screen. That sucks. And that's how my OKLCH version works. I just set up the lightness of the background color and the text color with a big enough difference. And regardless of the current hue value, this difference secures the readability of my interface. Let's now see the third superpower of OKLCH, which is uniformed chroma. Here are three labels of three colors. There is no contrast issue. All of them are well readable and so on, but one of these colors stands out. Can you pinpoint which exactly one? Red? Green? Yes? Green, yes, exactly. Because it's overly saturated as compared to the red and blue. You can even tell it by looking at the second parameter of OKLCH notation. The value of chroma of the green color is way higher. You know what? Let's give HSL the last chance. Maybe he can explain this difference. I'm going to convert OKLCH notation into HSL notation without changing the colors itself, and see if HSL can tell why this green looks a little bit different than others. Here they are. No, it can't. It says that all of them have the same saturation value, and maybe my eyes are deceiving me. Thank you very much. You are being very helpful, HSL. Let's get back to OKLCH. I don't like these colors be different. I want them be members of the same family, look consistent. And OKLCH gives me the exact tool that helps me to do this. Everything that I need is just set up the same value of chroma to all of them. And here they are. You might dislike this green now. It's kind of washed out and so on. That's okay. That's okay. OKLCH just gives us a ruler. No other color model has. And whether to use it or not is totally up to you. The last thing that I wanted to talk about is 50% more colors that I promised you if you switch to OKLCH today. Where do they come from and how it's even possible? Well, normally, without any conditions, human eye can perceive much more colors than any display technology can offer. This color blob calls CIE 1931 color space, and it roughly, with a lot of simplifications, represents the whole range of colors that our eye can see. And the current display technology has their own limitations, and they cover only small portion of this blob. You remember this slide, right? About red, green, and blue subpixels. But what exact red, green, and blue are used for subpixels? Well, older screens were capable of not very deep and rich red, green, and blue. So they covered very short, very small segments of all possible colors that we see in real life. And this tiny triangle calls sRGB color space. Color models such as HSL, HSB, RGB defines a color inside this sRGB color space. And sRGB color space is quite old. In fact, we use it for almost 24 years, more than 24 years. A quarter of a century, in fact. You know what was released roughly at the same time? Nokia 3310, ladies and gentlemen. sRGB is that old. In fact, Nokia is even younger. But time goes on, new technologies come in, and modern displays are capable of much richer and deeper colors, and they can produce more colors. This enlarged triangle represents P3 color space. And notice how bigger it is as compared to older sRGB. Not impressed yet? Well, take a look at this gorgeous, rich green in sRGB color space. Looks nice. And this is P3. Much deeper, much richer, much gorgeouser. Here is orange or red. I bet that you never thought that your red that you see every time in your graphic editor is kind of washed out before I compared it to P3. One disclaimer. This screen, as I said, it sucks. It doesn't adequately reproduce colors. So please go to OKLCH.com. You can do it right now. And check the real difference between P3 color and sRGB color on your smartphone or laptop. This is a color picker my colleagues created for your convenient exploration of OKLCH, so please use it after this talk, I hope. And all modern smartphones and laptops have supported P3 colors for years. And all these rich, saturated, I don't know more epithets to this, vibrant colors, they are all inaccessible if you use RGB, hex, HSL, HSB notation. Like, forget about them. Forget about making your websites look juicy on iPhones and MacBooks and any other modern devices. As long as you use sRGB color space, you belong to Nokia 3310 era. I'm sorry about that. Meanwhile, industry-leading companies such as Versal are adopting OKLCH and P3 colors right now. Here's the tweet by the Versal designer where he's showcasing their switch to OKLCH in order to get richer look for their landing page. So what are you waiting for? Give OKLCH a try in your next project. Before I go, I want to demonstrate my demo once again and repeat the statements that I made at the beginning of this talk. OKLCH keeps the contrast and readability of the interface consistent, regardless of the current hue value. It also allows you to build interfaces with dynamically adjustable colors. It might be user settings, for example, that your end users might use for setting up the exact color that they love. Or you can retrieve primary colors from image and colorize the interface to match them. And that will help you to build like smooth-looking product cards, for example. Doesn't it look cool? And OKLCH is the only one color model so far that gives you this opportunity without tons of manual work. And that's all OKLCH. Thank you very much.